100 other times we are going to ICNSR. Today, the first major conference on nonlinear dynamics we organized here in ICNSR. It was the first perspectives in nonlinear dynamics. So, Professor Ramaswamy has had a very distinguished career. He was one of the first people to work in nonlinear dynamics in our country. And am I perfect? If so, I will know my task. Or is it okay?
We can hear you.
You can hear.
Yeah, anyway, whatever she's saying, utter lies, utter lies.
No, absolute truth. You don't know what I'm going to say. So, he's one of the first people who started the nonlinear dynamics activity in the country, and he has been very instrumental in the fact that this activity is now at the level at which it is. So, I think we should all know that. He's had a very distinguished career. He was in Chiarpa, faculty member, he was in AU, he has been a School of Physical Sciences, he has been the Vice Chancellor of the University of Hyderabad. This guy and the other President of the Indian Academy of Sciences, President of INSA, various other things. And more importantly, he's a pretty good scientist and a pretty good friend. And I would like to introduce you to his talk, which is on synchrony as a constraint. Many of you will have heard of synchronization, and he's going to basically use the formalism of constraint systems to look at synchrony, which is a new approach to doing synchrony. So,
Thank you very much, Nilima. And it's a pleasure to be back at IIT and also a pleasure to give a talk in person. I don't know about you guys, I'm sick of Zoom. Even though I realize the irony of it, I'm on Zoom and off Zoom as I speak. You know, so life is cruel.
The audio is not clear.
Audio is not clear. Good
Now it's okay. When you come closer, it's okay.
Talking to you, is it?
Huh?
Oh, no. Okay, no, the thing is that we have. It's difficult to explain, especially to a box. All right, so I'll try to. Is this clear?
Yeah, this is fine. Thanks.
Okay, good. All right, so I'm going to have to pretend that there's one more person over here and then move on with this talk. Okay, the talk is on synchrony, and I want to view it in the language of constraint systems because there is an advantage to doing that, as I will try to show during the talk. But synchronization is a phenomenon that was discovered this is the outline of my talk. I'll give you a brief recap of what synchronization is about. I'll introduce you to the notion of generalized synchronization, and I will then talk in terms of manifold theory and what this whole business of constraint is about. Now, today, actually, synchronization is important even from a quantum perspective. There is this whole phenomenon called quantum synchronization, which is interesting. It has remained a generally interesting problem for a long time. And by long time, the original observation of synchronization goes back to Christian Huygens. The story goes that he was convalescing and he was seeing, he was in a room where they had a lot of these pendulum clocks that he had invented. And he noticed that when pendulum clocks were set off in motion, because they had to be wound mechanically, and they were just set off arbitrarily, after a while, they would turn to have synchronized, they would synchronize themselves, mostly that they would be either oscillating in unison in phase, or more often, they'd be oscillating out of phase. Now, he called this I mean, these are all now repeated so often that people, they call this oscillation in sympathy. And the feature of synchronization over here is that you've got two systems which are identical. More or less, they're the same system, displaced a little from each other. And the sympathy arises because they are connected by some, they're on a common beam or something. So they're coupled. Okay. So coupling plus fairly identical systems, and then we'll see what else goes into the whole idea of synchronization. Now, this has been studied, as I said, since 1600 and something or the other. But in the last 30 or 50 years now, the problem has resurged because of the interest in nonlinear dynamics. And the sort of origin of these questions could, we can sort of summarize it in this. Huygens saw the synchronization of pendulums undergoing small oscillations. As we know from enough physics, these are linear systems. They're approximately linear systems. These systems were also placed on a common platform. That's all that was done to couple them. So the question is that these are weakly coupled, almost linear systems. And the motion that Huygens noticed was periodic. But as we have observed in the last 50 plus years, most systems are not linear. Most systems are not almost periodic. And I mean, coupling can be strong or weak, that doesn't matter. But the fact that systems can be non-linear and not periodic, it begs the question, since most systems are chaotic, sensitive to initial conditions, etc., how does this idea push when we go into looking at nonlinear systems? So this was a question that people started asking in the 70s and 80s. And the sort of landmark paper in this area appeared in 1990 or thereabouts. Landmark because it appeared in physical review letters, and it was it was an implementation of an idea that had been seen elsewhere, but it was the following, right? That you take two systems that are identical and you feed the signal from one to the other, nonlinear, chaotic, and they synchronize. All right? So I'll come back to all this, so we'll see this. So since the 80s and 90s, this synchronization of coupled chaotic systems has been an important area. And what is interesting is how these two systems, when they are coupled together, drive each other into, well, my notion of synchronization is going to change a little. So how they become correlated. And given the fact that there are so many people with so much computing power available, people have gone to town. You've studied a whole lot of nonlinear systems. They've looked at all sorts of different kinds of coupling. They've looked at, you name it, chances are it has been done in some university in Shanghai, right? Like almost any other field, there's been some work on every topic. Okay. Also, since 1990, the notion of synchrony has expanded. Huygens saw, just to again give a caricature, Huygens saw stuff going either out of phase or in phase identically. But people have seen that when you couple systems appropriately, you could find stuff which is, the motion is the same, except that there's a time lag between the two systems. All right? So this is what they call lag synchronization, not surprisingly. Then another kind of synchronization is where you're going in or out of phase, but the amplitude of one and the other is uncorrelated. So the phases are correlated while the amplitudes are uncorrelated. So you call this phase synchronization. And then there is an industry that it starts looking at, if I do this, if I add time lag, if I do, whatever, whipped cream, whatever you can do, you add and you see, you call it some new name. So then at some point you get tired and you say, look, there must be a very general notion of synchronization, and this general notion is called generalized synchronization. Okay. What is generalized synchronization? The idea of generalized synchronization is just what's there in the first. The basic notion is this. If I say the two systems are synchronized, of course, if they are identical, I can see the synchrony visibly. But I'm willing to expand the notion and say that there is a map, that is a functional relationship between the variables of one system and the variables of the other. This functional relationship or this map can be the identity map. Namely, it could be that this is equal to that. But I'm willing to allow myself to say that there's a functional dependence without necessarily demanding that it be the same, right? So the cartoon on the right over there, if X and Y represent the variables of two systems, and that little parabola there represents the coupling, then the implication is that whatever the dynamics of Y is, it's some functional, a unique functional of X, right? And we'll see that it has to do with dimensions on manifolds as well, all right? Now, let me just go back over here. One. Correct. The fact that you have correlations between two systems says that implicitly the dynamics occurs in a lower, you see the fact of that the relationship over there, I'm going to be interpreting it as a constraint. Y is some function of X. And this means that the dynamics of that could have occurred if X and Y were completely uncorrelated, they would have occurred on some space. But because they are correlated, the whole dynamics occurs on a lower dimensional submanifold of the allowed space. And the other part is that it is an invariant submanifold, namely because it's a unique functional that y is equal to phi of X, then no matter where I start in Y, I must get onto the same functional dependence, and therefore this submanifold has to be invariant. All right, so okay, to some of the disadvantages of doing a hybrid with Zoom is that I can't write on the Zoom screen as I would have wanted to. So, now this is the synchronization between systems, dimensionality and the submanifolds play a major role, all right? So why is this? Supposing you have the two systems have got dimensions n and m respectively. The overall motion, if it is completely uncorrelated, takes place in n plus m dimensions. In this m plus n dimensions, all right, you ask how many of these directions are stable and how many of them are unstable, all right? If you've got, just take one system, like it's in n dimensions. If all the n dimensions are unstable, then the motion will fill this n-dimensional space completely. If all the m dimensions of the m-dimensional system are unstable, it will fill an m-dimensional space completely. So take the two of them, don't couple them or anything, but just look at them jointly. You've got n plus m dimensional. Now, if there are n prime and m prime unstable directions, okay, you would expect everything to be in this higher dimensional subspace. But if you are in an even lower space, I will say that this is synchronized in some sense. So the last statement over here, two systems can be considered to be synchronized in some sense if the resulting motion is confined to a subspace of dimension lower than the total space available to you minus all the unstable directions. Okay, to give an idea of, you've got these two pendulums, all right? Each pendulum is in two dimensions, theta and theta dot. You've got two, theta 1, theta 2, it's a four-dimensional space. When these two are moving together, theta 1 is equal to theta 2, theta 1 dot is equal to theta 2 dot. That's why they are completely correlated. So the resulting motion is on a two-dimensional subspace. I mean, I'm sorry to be so sort of explicit pedagogically, but you get the idea, right? That you're in a lower dimensional subspace, and we'll see what the implications of that are. Okay. So in general, if I take a graph of one variable versus the other, right? And a little bit of this is illusory because I'm dealing with two coupled three-dimensional systems. All right, so the actual space that I'm looking at is 6 dimensions. The two signals on top are uncorrelated. It is not synchronized at all. And I'm just looking at a two-dimensional subspace of that plot of x versus x1 versus whatever. And you can see that it's a complete mess. Given enough time, it's going to go over that entire space that is allowed. But in the entire 6-dimensional space, it would have done it over the entire 6-dimensional space. Right? The second figure that you see over there is what's called phase synchronization, where the phase variables of the two systems are highly correlated. And we can see that there is an obvious correlation between them, in the sense that there is a unique lower dimensional space that is getting covered by the entire thing. And in the last example, there is actual synchronization between the two systems. The signals are identically on top of each other. And when I plot x1 versus x2, I'm just covering a one-dimensional submanifold on this two-dimensional space. But essentially, it is a three-dimensional submanifold of the six-dimensional space. Yeah. Okay. So this is okay, so that's actually the talk. Bye bye. Thank you very much. You've got to think of the entire process of synchrony as a way of constraining the system. Right? Now, one of the things that we learn when we do constraints, when you look at constraints in classical mechanics, is that there's some familiarity with classical mechanics 101 or earlier courses, I don't know. See, each constraint reduces your dimension by 1. So the whole effect of, I mean, I'm putting it the other way around. Now, when you see that the whole thing is on a lower dimensional manifold, I just want to see that what has happened to make these systems lie on this lower dimensional submanifold is a set of constraints. What are these constraints? Okay, so now a little mathematics. We'll consider two coupled dynamical systems, one with the variables x, the other with the variable y. And zeta x and zeta y are the coupling functions. All right? So when I set them equal to 0 each, this is uncoupled systems. And I don't care, let's just take them to be distinct. I've already told you that the idea of generalized synchronization is that y is a unique function of x. So that is going to now define my constraints, right? Now, in this business, there is a type of coupling called master-slave coupling. Namely, or in mathematical terms, it's what's called as Q-product systems. X evolves on its own, and y dot is a function of x, y, and maybe some coupling strength epsilon. And it has been observed in lots of earlier studies that for suitable coupling epsilon, there can be generalized synchronization where the slave y, the slave or the response, is a unique function of the drive. And the way in which this was and the way in which this was observed earlier, yeah.
Sir, is it a special kind of system or special case, or any general system can be reduced into that kind of?
This is a special case. You will see that actually I'm going to come to an extremely general formalism as we go along, all right? Okay. So this, how do you check that you have a unique functional relationship between the drive and the response? It's very simple. You make two copies of the response. You have a drive acting on response 1, it gives you some output. You take the same drive, apply it onto another response, and you get another output, and then you check the two outputs. If the output from both responses is the same, then the drive is affecting the response in a unique way. Right? So this is traditionally how one used to detect generalized synchronization. You have a drive, response 1 gives you some signal, response 2 gives you the same signal. And then, therefore, the output from response 1 and the output from response 2 should be perfectly in synchronization. So this is how it was. And this can be seen in some sort of very, very simple cases. For example, if you take two coupled maps, and you can see the example over here, right? So this is the mapping in question. You've got the X system, it just depends on the variable X. The Y system depends on the variable Y, the same map, plus a coupling term. And I have a copy of the Y prime variable. I'm doing the hybrid and living simultaneously in two different planes. Okay, so you've got, and you've got the coupling over here. So you see, it's the same drive. Okay. Now, for some value of epsilon,
I'm not sure what the guys on Zoom are saying.
huh?
I'm not sure what the guys on Zoom are saying.
We don't care. Okay, so right on the first line, you have basically uncoupled systems. It's filling up this two-dimensional space completely, right? At a certain value of epsilon, the X and Y have a complex relationship, but it is unique because if you look at Y and Y prime, it's perfectly synchronized. That is, the two copies are identical, even though the dependence of Y on X is complex. And then if you increase the coupling more, X and Y become identical, right? So they are oscillating together, and Y prime are also. So this is the 1996 or something, you know, in the dim and distant past. Okay, so okay, this is not that important. Okay, so the idea of the synchronization manifold is this, that this is a invariant subspace in phase space, and it has a lower dimension than the entire phase space. And for it to be interesting for us, really, the dimension is much lower. A 5-dimensional submanifold of 6-dimensional space is still going to have really motion that is not that doesn't look as correlated, Now, if you, okay, so I'm going to sort of think of it in, as a plane, let's say in a 3+ something dimensions, all right? You want this synchronization, you want the motion on the synchronization manifold to be confined there, which means that if I have perturbations away from it, those perturbations have to die out very fast, okay? Now, this submanifold should in some sense be smooth. You'd like that to happen because if it's not very smooth, these are all going to be, from an engineering point of view, and since I'm speaking at IIT, the engineering applications are not uninteresting in this, as you will observe shortly. All right. So again, to repeat myself, that's what it is. This is actually not difficult to engineer in some ways. So if you've got those two systems and a particular relationship that you want y is equal to phi of x. So you would like phi of x minus y to be equal to 0, right? You can design the coupling in a sense as simply as this. I can take the x coupling function to be 0. So x is not affected by the motion. And if I take y function to be something like this, then a little fairly straightforward and trivial algebra shows that this function d by dt of phi x minus y is just minus some constant times phi x minus y, which says that this is exponentially attractive. But then you see what happens. X dot is equal to f of x, but y dot, which was f of y, looks nothing like, the coupling has subtracted out the essential flow, it has done all these funny things, but this will give you the required relationship, except that it destroys the system completely. And this is not what we want to do in terms of synchronization. What one would, okay, so our procedure is the following. Okay. Supposing our functional relationship phi of x, see, I've given, where is this? Okay, so I want this phi of x, I want y to be equal to phi of x, right? So these constraints, I define them as some n-dimensional vector of constraints. The basic idea that we have is geometrically like so. In the phase space, if the synchronization manifold is defined by the surface that you see over here, what I want the coupling to do is to bring me onto the submanifold and then keep me on. For that to happen, if I take the surface and define the normals, the flow on the manifold should be orthogonal to the normals. And this should be orthogonal at all points in space. Okay, so this is just the basic geometric idea that you have. You've got a surface, define normals everywhere. The flow just should be orthogonal to it at all points, as you can see from this schematic diagram. So if you happen to be at this point x, the first thing is to bring it here and then keep it over here. So all the forces, this is not easy to put in the language of forces, but all forces that we have should be acting perpendicular to this, like forces of constraint do. Forces of constraint don't affect the motion at all. Even, they're infinitely in the forces are infinite in some directions, but they don't affect the motion of the system. Right? So, all right, so this is basically the idea over here. Along this submanifold, you just define this vector of normals. You want these normals to be orthogonal. See, the flow equations are given by, f of x defines the flows. This is the normals, and so you've got a matrix equation which specifies that, all right? And given that particular identity, you can deduce the coupling, the zeta coupling that is required can be deduced from that matrix equation. One problem is that this is not a unique solution. You can get more than one solution because these are not square matrices, right? I mean, when you sit and work out the examples, these are not square matrices. You do get multiple solutions that are possible for this particular case, right? And the other part is that you don't have unique solutions because any other coupling that vanishes on you can add extra terms, but if it vanishes on this submanifold, doesn't make a difference. Okay, and we are familiar with these kinds of algebraic constraints in a variety of mechanics problems, right? That you do have systems where you can keep adding extra terms. You can add a perfect differential, it doesn't change the Lagrangian, for example. Okay, so this is not an unknown thing. All right. Okay, and in order to make sure that this whole system is stable, we would like that once you're directed towards the submanifold and kept over there. All this and more is revealed in this paper in Physical Review E. Okay. Sometimes the best thing is to just show a couple of examples, and you will see what I'm trying to. What is the point of this? Okay, you take two Lorentz oscillators. Okay? These are typical chaotic systems. Everyone has seen them, screensavers, etc. So the left-hand side is the X system, X1, X2, X3. The right-hand side is the Y system, Y1, Y2, Y3. Okay? When they are uncoupled, they're just all over the place. They are completely uncorrelated. I want to, okay, my target aim is the following condition. X1 is A times Y1, X2 is B times Y2, and X3 is C times Y3. If A, B, and C are 1, this is identical synchronization. If A, B, and C are arbitrary, it is whatever it is. Okay. Now you put in this constraint. So those are the three constraints. Put it through the algebra that I have just sketched out to you. It exists. Okay, there's an algebraic procedure. And that comes up with the following coupling. This doesn't destroy the two systems, but it couples the two systems in some nice way. For any value of A, B, and C, if I just do that, you find that, okay, that's your original system, and that's the Y system. I arbitrarily gave X, A was 1, B was 2, and C was 3, or something like that, you know. So you can see that I can just blow it up, you know. Okay, so that's one. Turns out that the systems don't even have to be identical. See, I started out with two identical Lorentz systems. And instead of taking two identical Lorentz systems, if I take, you know, systems which are not very, meaning you can really play around with the equations of constraint and just bring it onto that required submanifold. Okay. Here's another example. Okay, so this example is where you've got x1, y1, sorry, x1, x2, x3 was one system, y1, y2, y3 was another system. What coupling will cause the variables to interchange? So I want x1 to be equal to y2 and y1 to be equal to x2. So that sort of flips the two. There's a coupling. There are many couplings that will do it. It's not unique. But here, for example, is a coupling, and this is what it results in. And you can see that you've taken a system and just flipped it around onto itself, and you've got a way of changing the identities of variables, if you like. Okay, and here is an example that might illustrate a little better what these, the sort of the power of this kind of thinking. This is the relationship that I would like between y3 and x3. I want y3 to be equal to x3 squared. Very briefly, so far, what we have done is we have taken a target submanifold which was flat. A times x1, B times x2, and C times x3 is just a plane in this six-dimensional space. And this plane was just at different angles, but these are all flat surfaces. Now I want to make a parabola. I mean, two of those dimensions are flat, but in the other one it is curved. And there's more than one way in which you can do this. So one way is to say that x3 is the square root of y3. The other way is to say that y3 is x3 squared. And it turns out that, and as you were asking earlier, that it's your choice. You can choose zeta, that is the coupling of one system, to be 0, which means this is the master. And that's the slave. And you can see that, you can see in the phase space, you've just pushed yourself onto a curved manifold over there, right? And, you can again see that the square, the variables are just squared in one dimension. But I can do it in two different ways. I can make this the master and this the slave. And that gives me the blue curve. And I can couple them both to each other, and that gives me the red curve. All right? So you've got this manifold, and different couplings push you onto different parts of this manifold. Okay? Now, you can try to implement this, and you can implement this in circuits. We did it in, one example was done with some people in IIT Kharagpur, but I'm hoping that we can do slightly better. Oops. Okay, so this is Soumitra Banerjee's group in IIT Kharagpur. They did this coupling, that I just showed you with electronic circuits, made examples, and they got things, reasonable. But I'm trying to persuade colleagues to do more of these kinds of tests. Okay, so, let me push along to a more interesting case. So you get this idea that we have over here. You've got a set of constraints, you decided what they are, and you ask what is the coupling that can bring you down to them. Can you do this in spatial freedoms? Namely, can you constrain two systems to be moving through, let's say, a three-dimensional space, keeping a fixed distance from each other? We had these equations of flow equations, but what happens if these are now moving in some space? Right? This is a bad video edit, but let me try to since I spent so much time. Okay, so this is an example of rigid body motion. I love this part of Kubrick's movie. But okay, so you've got a rigid body which consists of 10 to the 20 particles. They are moving around in three-dimensional space. The total number of variables should be some multiple of 10 to the 23. But essentially, you can describe the entire thing by 5 variables. 3 positions, 2 orientation angles, and that's that. So the effective reduction in dimension is huge. And that only happens because of the huge number of constraints that there are. Another example of how spatial constraints and let me just show this first. The phenomenon called murmuration. A darling of the YouTubes. All right, so here you've got this bunch of birds. Okay, so there may be 1 million or so birds, and they are flying in a three-dimensional space. And okay, so this is a biological phenomenon where all these birds are flocking. There's obviously a high level of correlation between them. And the point that I just want to say is that this is not as rigid as the bone that we just saw that was being thrown, but this is not 1 million degrees of freedom problem. Much, much lower. And if you if you look at the actual tracks of these of birds, this is by a photographer called Xavi Bou in Barcelona. What he does is he takes pictures of birds and then does time-lapse video editing. And you can see now that these birds, as they are flying, first of all, they are highly correlated. Obviously, they don't want to be hitting each other as they're flying through a three-dimensional space, but also observe that the beats of the wings, as you can see them captured in image over here, these beats are also highly correlated. Right? So, I mean, there is some very strong degree of stuff going on over here. Well, okay, so the idea is this: how do you get two systems to be correlated in 3 dimensions with other motion going on? All right. So to start with, we said, all right, if I've got 2 systems, these are some 2 simple oscillators, can I make my constraint such that the distance between x1 and x2 is A, and the distance between y1 and y2 is B? Right? Distance, separation between x1 and x2. I mean, these are obviously not moving in 3-dimensional space, but still, mathematics is fun. So you can do it. All right, and you can do it very simply. Those are the kinds of couplings. And again, we use the master and the slave kind of paradigm over here. And so this is your one van der Pol oscillator, and that's the other. It's just shifted by whatever distances you decide you wanted them to be shifted. Right? You can take chaotic oscillators and again shift them out by required amount. But more fun, supposing I just have stuff that is moving around in space in some arbitrary trajectories. I'm just building up to what I want to actually study, right? Oops. So here is, okay, I'm going to play it again, right? This is a bunch of n particles moving around in three-dimensional space. The essential motion of one is, let's say, the blue curve that you see out here on the left. All the others are decided by putting fixed distances between each other. I'm not saying birds fly like this, but I'm just saying that supposing there is one bird that decides that I'm going to figure out some particular path, each other bird walks a certain distance or flies a certain distance away from them. And there is jitter, there is noise. I mean, we play around with that. But you see, you can make them all fly in the way which sort of mimics murmuration. Okay, the constraints over here are time independent. I've just said that the distance between 1 and 2 is A, 2 and 3 is B, 3 and C, whatever, and so on. In very recent work, we've shown how to extend this completely. So we can make the distance between 1 and 2 change in time, 2 and 3 change in time, and so on in a specified way. But that's the thing. So where would one use some idea like this? Okay. Birds are not going to be obeying our motion. So the obvious place to use it is in autonomous vehicles. So luckily I have a laboratory in IIT Delhi. It's a startup company called BotLab. And so they make drones. And some of you might have seen their work on the beating of the retreat in Delhi this year. They had a drone display with lights. I cannot claim that they were using our algorithms over here, but we work reasonably closely with them. So here is an example of 3 drones using constraint dynamics. One of them, I think it's this chap over here, is the master. The second drone has the fixed distance from the master. The third drone has the fixed distance from, again, 2 different distances. Okay. Well, I mean, this is just a video taken from the ground, but it uses our algorithm for controlling the flight of these over a fairly large area of space and so on. There is an unidentified object that flies over there, not being controlled by me. But okay, so the other 3 are basically in complete unison using our methodology. Right? We haven't been able to, we haven't gone to thousands or what have you, but this basically gives you an idea of the power of this kind of thinking, that you constrain systems using ideas of geometry and bring them down onto lower dimensional subspaces. Right? Okay. So let me summarize. What I've tried to show is that all kinds of synchrony, anything that you call synchrony, is essentially or can be viewed as a process of constraint. And the coupling is what gives you forces that will bring you into this fixed relationship with one another. By its very nature, the whole process of synchronization is not unique. This has been known for a long time because different ways of coupling systems can synchronize. sort of different algebraic ways of coupling systems can synchronize them. But when you study this in a more geometric and more mathematical form, you see, we are seeing it now as a control problem. How do you control two systems so that they lie on some invariant subspace? And then there are other interesting ideas about stability and geometry and so on. Manifold may not be globally attracting. In fact, there could be, there could be interesting dynamics within this particular system. And in the examples that we have seen, so long as you have reasonably smooth constraints, okay, what I showed you was a flat manifold or quadratic. I haven't really played around with very complicated kinds of spaces, but at least for this gives you a high level of control, and you're able to design a fair amount of, a fairly efficient synchronization couplings that in this particular system. Right. Okay, and with that, actually, let me tell you that as I already acknowledged, there was a collaboration with Botlab for the drones, Banerjee and students at ISER Kolkata, and in my lab, Vishal, Shahrukh, and Amrita. And thank you for your attention. Yeah.
Information input is stored, they are invariant. They are invariant with respect to inertial flow.
There is not necessarily energy, there is invariant with respect to flow.
So, sir, so far, all these properties, they are somehow, are they somehow related to nonlinear conformables?
No, they're not really. I mean, many of the language is similar, all right, but it's not actually related to normal modes, because normal modes is a unique problem. Given you linearize your system, and then you will get a unique set of normal modes. Here, all you have done is that you've asked for the flow to be orthogonal to the normals to your manifold, and that gives you actually a set of highly non-unique solutions.
Between those lag synchronization and desynchronization, they are both like combination of normal modes. The results.
They look like it for simple cases, right? But there could be many examples that come beyond those two simple cases.
Ram, one could probably write it into.
What is the normal modes? I am not so sure, because normal modes requires almost linear systems, right?
No, but see, you could actually go to the synchronization, and you could in fact linearize about the synchronization.
If you linearize, the linearization about the synchronization manifold, you do it for the stability.
No, you could also actually do this kind of thing, right? In the case of you actually look for the stable manifold, the unstable manifold, and the neutral manifold. The neutral manifold is in fact the perpendicular to that to x equal to. So one could perhaps.
See, I'm seeing this almost as a design problem.
But one could do this given as you could just take the same system of it and then see what it is.
So maybe something to think about.
Yes, so when you are finding these coupling functions that give you the desired invariant manifold, you also need to check that they're stable to transistor. So there will be non-unique coupling which all give you the same stability to transistor. That's possible.
So that's the immense flexibility of this kind of. That's why I showed you those three different ways of coming to that same, the curved space, the quadratic constraint space. Three totally different ways of doing it.
And the converse problem, like where the coupling is given, it would be not a trivial task to find the invariant manifold on this.
No, that is, once you're given the coupling, you go where you go.
So, but would that still be a unique problem?
Could be, need not be. I mean, see, once you're given the coupling, what results is what results. Here we are sort of forcing a certain kind of result by
Asking for the coupling.
asking for the coupling.
You may not get it.
How do we distinguish between synchronized systems and integrable systems?
Okay, I think I understand where you're coming from in the sense that integrable systems also have a bunch of constraints. You have as many constants of motion as you have number of freedoms. Synchronized systems are not, okay, they don't have, if you had as many constraints as you had degrees of freedom, you would be sort of in a sense hyper-synchronized. All I want is that n plus n, which is the number of constants should be somewhere less than the number of unstable directions. For integrable systems, you need them to be as many constants as there are freedoms. Okay, so that's even much more constraint.
What happens if we have two different systems, like Lorentz and Moore? Can we do almost?
All of this works unscathed for. Actually, this doesn't. The identity of the two systems is not there. Once you've written your equations, the question is, can you find a solution? Because it's an overdetermined problem, you will have many solutions. And they may not all be stable. There could be problems associated with that. So, I mean, those are algebraic problems, but in principle,
Your question. So what does it mean to synchronize two completely different?
okay, so my general idea of synchronization is just to say that if you couple two systems, okay, the qualitative part is to say that you don't destroy the system completely, but you couple them such that there is a unique mapping between the variables of one system and that of the other. Then I'm willing to call it synchronization. Is this what Huygens did? Probably not. Is this even what normally we will think about as synchronization? Maybe not. But this enlarges the scope of synchrony in a way which I think is quite useful. It includes all the earlier examples, but now it gives you a set of different, are birds synchronized when they are flying? In some way, of course they are. Otherwise, but when you see that the starlings, you can see that there is a lower dimensional manifold over there. Significantly lower dimensional manifold over there.
Yeah, so the last part that you're talking about is mobile problems. So is the challenge more computational in nature that the method I'm assuming remains the same?
Yeah.
So is it an implementation of finding that coupling function which amongst so many others?
See, for drones, for example, the big challenges that I feel that we have to tackle is that these are subject to big perturbations by the medium in which they are, the flow medium. As your drones are going up and along comes hurricane, whatever, or rain, or whatever, so how do you keep these things stable under big perturbations? How do you find the right ones to optimize and so on? So these become big challenges.
And for those, standard large number of coupled oscillators, people usually take the approach of writing a mean field version of that.
Yeah.
Can that be obtained from, like you say that this is the synchronization I want? Is there an equivalent mean field form that I can find? instead of the individual coupling?
I honestly I haven't thought about it in terms of a mean field because I don't know over here, so I haven't thought about it as a mean field problem. I'm not entirely sure it can be done, but I'm willing to think about it at some point.
In the drones, how your schedule coordinates with the GPS?
Yeah.
So, if you were talking about perturbation, so I have been trying also, so I know that. So, can we keep some local coordinate system like one device and some infrared rays or something that can have some, we can measure the distance between them and instead of using GPS, because some, some accuracy.
No, absolutely. Yeah. I mean, this is the kind of stuff that we've been trying to get them to do. The GPSs keep the distance to within a meter or not much more than that. So keeping the constraints for the beating of the retreat problem, it looked like 1,000 drones flying together. There were 1,000 drones flying individually. Just visually, they looked as if they were together. Right? They were not using our method for that large number because they just couldn't fix some of these problems. All right, but I mean, think of how you can. You see, when you've got depending on the kind of task that you think that you would like to carry out, if you need two of them to be highly correlated, they have to communicate with each other. Not that this communicates to the ground and this sends out a signal to the second one. This lag is too much. So, I mean, these are practical problems which have to be sort of resolved. But you're right, we use GPS and this infrared communication between the two. I don't know whether we have that or not, but so far it has been drone 1 to ground to drone 2 to ground to drone 1 and back and forth.
So if I tell everyone to follow some beautiful but I add some sort of a cost or a recursive potential for them to do. So this is not a master slave model, but all of them are sort of following some rules. Is that a fair use?
That's a fair use. The little example that I showed you of this one following this thing is very similar to that.
Yes.
Very similar to that. It's just an arbitrary geometry in space, and you've got this bunch.
How do you differentiate like swarming and
It is swarming. These are swarming algorithms.
yeah. So that's like it is different from swarmulator.
It's different from swarmulators because there is no repulsion between two systems. Swarmulator, the potential, like whoever was saying, they can't come too close. Here, I'm not making them recognize that they are coming too close. I'm just saying that distance 1 minus distance 2 has got to be equal to A. Right? So it's a little different from swarmulator, but I mean, many of these ideas do play around with that.
Maybe Ram, you could just put up your email ID. You have it on
I don't have it on this. Google me.